Okay, so the chapter 6 problem is, heat engine, refrigerator, heat pump. Might be regular, might be Carnot, might be both, because like this one, part C is saying, hey, what if this was Carnot, or hey, what's a maximum pop, what's the best possible? Alright, so this is a tough one. I think it needs some explanation. Alright, refrigerator system uses a water-cooled condenser for rejecting the waste heat. Alright, so you remember those, that kind of diagram for a refrigerator or heat pump that has, so let's go this way, that has refrigerant going through these tubes, and there was an evaporator, I think compressor, the condenser, and then like a throttling valve or something here. The Q, let's see here. The QL was going in here, the QH was going out here, and sometimes it spits the QH out into the air, out behind the refrigerator, right, into the atmosphere. But this one, all it says it uses a water-cooled condenser. So there's refrigerant. Refrigerant is probably still the working fluid going through here. But instead of spitting this QH out, it's almost like a heat exchanger. It has water coming in, water out, and the Q is going into the water. Right, the Q from the refrigerant, QH from the refrigerant is going to the water, and so this temperature down here, TL, would be, I think it said 25 degrees, but the TH is going to be the temperature of the water. Not the temperature of the air, not the temperature of the atmosphere, not the temperature behind the refrigerator. This is going to be the temperature of the water, TH, right there. Okay, so anyway, with that explanation, I think kind of the hardest part for these problems is kind of just telling us, all right, this 25 degrees that it gave me, is that TH or TL? This 24,000, is that QH or QL? This temperature, that, okay. So let's kind of decipher this. The system absorbs heat from a space at 25 degrees Fahrenheit and 24,000 BTUs. That is the TL and the QL. TL and the QL. The waste heat in the condenser is the TH and the QH. Then it says water enters the condenser up here at 65 degrees Fahrenheit at a rate of 1.45 pounds per second. The COP of the system is estimated to be 1.9, specific heat of water 1.0. Determine the power input of the system, temperature of the water at the exit, maximum possible COP of the system. Okay. So we have a few equations. One of them is COP for refrigerator is QL over WN. And I have the COP, I have the QL, I can find the WN. So let me start with that. 24,000 BTU per hour divided by WN. I would get the WN as BTUs per hour. I could leave it not possibly as BTUs per hour. Yeah, sorry, let me do that. 24,000 divided by 1.9. Oh, yes. 12,631.6 BTU per hour. Yeah, but it wants it in kilowatts. It wants it in kilowatts. So convert that to kilowatts. The WN 3.70 kilowatts. 3.70 kilowatts. Okay. Now, if you didn't know that you needed to find this, you know, then I've got an equation. You know, once you've got the work and the QL, you know, then you can find the QH. Well, work is QH minus QL. Generally, once you have two of these, you can find the third. And I've got two of them. Let's go ahead and find the third. QH dot, sorry, let me see here. Work, 12,631.6 BTU per hour. QL is 24,000 BTU per hour. All right, so QH, 36,631, or let's say 632 BTU per hour. All right, so that is the QH that goes out of the refrigerant and into the water. Q, the heat transfer that goes out of refrigerant and into the water cooled, right? The water that is cooling the refrigerant. All right, this is like a heat exchanger right here. The QH that's leaving the refrigerator and leaving the refrigerant is going into the water. The water comes in at 65 degrees Fahrenheit. What does it go out as? What does it go out as? And I was given the specific heat. So M C delta T, right? Does that make sense? That the Q, so now I'm looking at the water. The Q for the water, the 36,632 BTU per hour equals M dot, 1.45 kilogram per second. My units are all whacked, all messed up here. The CP for water, 1.0 BTU per pound mass degrees Fahrenheit. And the temperature change, I don't know. That's what I'm trying to find. That's what I'm trying to find. All right. And I apologize, I don't have this. My units are off. I've got kilograms and pound mass, and I've got BTU. These are all out of whack. There's some unit conversion here. And some unit conversion, which I don't really have. All right. But make sure the units on the right-hand side equal the units on the left-hand side. All right. Make sure the units on the right-hand side equal the units on the left-hand side. All right. I've got T2, 72.02 degrees Fahrenheit. T2, 72.02 degrees Fahrenheit. Okay, so actually, all right. All right, so this water that's entering the condenser enters at 65 degrees. The water that's exiting exits at 72.2 degrees. So the TH, the temperature that the refrigerant is rejecting the Q out into, some of it's rejecting out into 65, some of it's 72, some of it's in between. Let's use the average temperature of the water, 65 and 72.02 divided by 2. Let's see, what is that? 65 plus 72.02. 68.51. Okay, sorry. All right, sorry. That is the answer to part B. Now I'm trying to find the answer to part C. And so in order to do that, I want the TH. So that is the TH right there. So that I can part C, coefficient of performance for the refrigerator, if it's reversible, 1 over TH over TL minus 1. So yeah, that was my problem. I was trying to figure out, okay, I know that the TL is 25 degrees, but I would need to change it to absolute. So plus 460. And my TH was, what temperature am I rejecting the waste heat out into? It's going out to the water, and the water, so it's at 65, it's leaving at 72. So in general, it's leaving at a temperature, it's rejecting waste heat to a temperature of 68.02. So this would be 1 over 68.51 plus 460 over 25 plus 460 minus 1. 1 over that whole thing. Maximum possible COP 11.2. Maximum possible COP 11.2. All right, so that was the refrigerator. Sometimes the Q is M delta H. This time delta H was C delta T. This is a tough one. I don't know if we've done one that has a water-cooled condenser, but it's rejecting the Q from the refrigerant into water instead of into air. And the water is coming in at a temperature of 65. We got to figure out what it's leaving. It's leaving at a temperature of 72. So the average temperature of that water, the refrigerant is rejecting heat into the water at about 68.5 degrees Fahrenheit. So use that for my TH for the coefficient of performance. That was a tough one. All right. That was tough. I don't know. Look at this next one. This next one may be a little bit more of the quality of the exam. But I think sometimes the hardest part is figuring out what that one is. Is that the QH or the QL? What that was? Is that the TH or the TL? This was a tough one because that was neither the TH or the TL. There's the coefficient of performance. And then also, what is it asking for? Is it asking for W? Is it asking for QH? Is it asking for QL? All right, and so it'll probably be a refrigerator or heat engine or heat pump. And I might ask, what is the best scenario? What's the minimum possible mass flow rate? What's the minimum power supplied? This one, what is the maximum possible COP? That's telling you, hey, if this was Carnot, this was reversible, what would this problem be like? All right.